walk into the roadmap room, and every wall is already spoken for. Product has its 3-year vision mapped out in colored lanes. Architecture has a platform modernization track with its own dependencies. And security has a single slide with the words post-quantum cryptography, PQC, circled in red. Everyone agrees that quantum will matter someday. No one in the room can tell you exactly when, how much budget it deserves, or what would trigger a serious move. The risk feels abstract, the timelines feel political, and the easiest move is to push the conversation to the next planning cycle. That quiet deferral is where post-quantum paralysis begins.
This is a Wednesday headline feature from Bare Metal Cyber magazine, developed by Bare Metal Cyber, and it is about leading through that kind of uncertainty. The real challenge for a security or technology leader is not predicting the exact year quantum breaks today's public key cryptography. The challenge is steering your organization so that a cryptographic shift can happen without blowing up everything else you need to deliver. PQC is not just a math change, it is a systems and governance change that touches long-lived data, trust infrastructure, vendors, and roadmaps that stretch over many years.
The uncomfortable part is that there will not be a neat calendar event called Q-Day. Adversaries will not send you a notice that your algorithms are now obsolete. Instead, quantum capability will emerge gradually and unevenly. At the same time, well-resourced actors can already harvest now and decrypt later, quietly recording traffic or exfiltrating encrypted data, with the expectation that future capabilities will unlock it. You are making decisions today about data that will still matter 15 years from now, yet most of your planning tools think in terms of quarters and fiscal years.
For a leader, that mismatch between time horizons is the real problem. Long-lived assets, such as sensitive intellectual property, health records, detailed financial histories, critical infrastructure designs, and state-sensitive communications, do not care that your roadmap is built around 2-year cycles. If those assets are protected by public key schemes that are likely to break in a quantum future, the exposure is real, even if the exact date is not. Later, when cryptanalytic progress becomes undeniable, many of your past choices will be judged through the lens of what did you know and when. That is why treating quantum risk as a distant science story is dangerous.
Complicating things further, standards and vendors are still in motion. The National Institute of Standards and Technology, NIST, is working through the standardization of quantum-resistant algorithms. Details about performance, key sizes, side-channel behavior, and deployment guidance are still evolving. Your cloud providers, hardware vendors, and networking stacks are all on their own timelines, driven by their own incentives. Betting everything on a specific algorithm, a particular vendor promise, or a speculative year is risky in its own right. You cannot truthfully tell your board that there is a fixed deadline and a completed playbook. The honest answer right now sounds more like this. Quantum risk is real for certain categories of long-lived, high-value data. The timing is uncertain, and the impact will be unevenly distributed across your environment. Some systems can adapt quickly. Others are welded to today's cryptography in ways that make change slow, expensive, or politically charged. When you see that picture clearly, you can stop asking for a calendar date and start asking a different question. Which decisions we make today create irreversible exposure for long-lived data tomorrow?
To answer that, you need to know where cryptography actually lives in your estate. When people first think about PQC, they often imagine swapping algorithms in a library. In reality, the hardest work lies in the places where cryptography is deeply fused with identity, connectivity, and uptime. These are your cryptogravity wells, the systems where keys, certificates, and protocols are so entangled with operations and third parties that any change feels like open-heart surgery. You cannot treat them as simple patch targets. They are trust infrastructures.
Public Key Infrastructure, or PKI, is a classic gravity well. Your certificate authorities underpin device trust, application identities, mutual transport layer security, or TLS,
between services, and sometimes entire machine identity programs. Identity providers, access gateways, and virtual private network, or VPN systems, are also heavily dependent on specific key types and protocol handshakes. If those components cannot support hybrid or quantum-safe modes without major redesign, you are not just adjusting algorithms, you are rethreading how users, workloads, and partners prove who they are. The casual promise that we will just swap in post-quantum algorithms later usually collapses when you look closely at how these systems are built.
Then there are the stubborn edges of your environment. Embedded devices and operational technology often ship with fixed cryptographic assumptions and limited update paths. An Internet of Things, or IoT, fleet in the field, a generation of medical devices, or an industrial controller installed for a 20-year lifespan may all depend on key types that become problematic in a quantum future. The same pattern shows up in core business systems like core banking platforms or trading engines, where cryptography is baked deep into workflows that require extensive validation and regulatory sign-off before any change.
Vendor and ecosystem dependencies add another layer. Many of your critical services are delivered by software as a service, SaaS, platforms, managed providers, and industry networks. They make their own decisions about when to adopt quantum-safe algorithms, hybrid key exchanges, or new certificate formats. Your contracts and integration patterns may quietly assume today's cryptography for the life of those relationships. If you do not surface those dependencies early, you will end up telling regulators or major customers that you are waiting on your providers at precisely the moment they want to hear a more intentional plan.
Once you start seeing these crypto gravity wells, the PQC conversation changes. It stops being an abstract talk about distant quantum breakthroughs and turns into a concrete map of where your trust foundations are likely to resist change. That map does not solve the problem by itself, but it does give you the raw material to move from fear or denial into a set of deliberate choices.
The next move is to treat PQC as a portfolio problem rather than a single project. The instinct in many organizations is to either declare a grand post-quantum transformation program or quietly bury the topic under more immediate issues. Both reactions are understandable, and both are unhelpful. A portfolio mindset says that different data and different systems deserve different levels of urgency, investment, and disruption.
One way to frame that portfolio is along 3 dimensions: how long the data must remain confidential or trustworthy, how interesting it is to capable adversaries, and how hard it will be to refactor the systems that protect it. High lifetime, high-interest data is where you should focus first. That might be sensitive research and development artifacts, certain defense or intelligence information, long-term financial records, or critical infrastructure designs. If this data is protected with public key schemes that are likely to be broken in a quantum future, then harvest now and decrypt later is not a theoretical slogan. It is a real risk.
At the other end of the spectrum, you have data and systems where the lifetime is short and the value is modest. A low-sensitivity internal experiment, a short-lived marketing campaign environment, or non-critical telemetry that ages out quickly may never justify complex PQC migration. The cost and disruption of change in those areas might outweigh the residual risk. The key leadership action is to bless that differentiation explicitly, rather than chasing an unrealistic uniform standard that will quietly stall everywhere. Practicality matters just as much as theory. Some systems are good early candidates because they sit on modern platforms, already have clean abstraction layers, or are being actively developed. Others are so tightly coupled or so bound by regulation that any change requires multi-year planning and external coordination. When you layer this practical reality onto your risk view, you can stage PQC work in waves.
In one wave, you might focus on reducing exposure around long-lived, high-interest data. That could involve applying quantum-safe or hybrid key management to archives and backups, or tightening the way high-value data traverses networks where traffic might be harvested. In a second wave, you might build crypto agility into new platforms and services, making sure that the things you are building now will not be locked into today's algorithms. A third wave could tackle the slow, negotiated shifts in your most stubborn gravity wells, where you know you will need regulators, partners, or vendors at the table.
This is where crypto agility becomes the central design principle. If you accept that there is no single Q day and no single migration window, the only sustainable strategy is to make your systems capable of evolving as algorithms and expectations change. Many organizations use the phrase crypto agility loosely, but their architectures tell another story. If application code directly chooses specific algorithms, hard codes key lengths, or embeds certificate details into database schemas, the system is not agile. It is brittle.
The architectural move is to treat cryptography as a platform service rather than an application detail. That means applications ask for things like sign this, verify that, or establish a secure session with this counterpart through standardized interfaces. The platform layer then decides which algorithms to use, which keys to call, and which policies to enforce. When you design around that separation, you can change algorithms, tune parameters, or introduce hybrid schemes without rewriting every consumer.
Hybrid patterns are especially important for PQC. A hybrid key exchange that combines a classical method with a quantum-resistant one allows you to de-risk early adoption. If the new primitive turns out to have performance issues or side-channel surprises, you still have classical security in play. Over time, as confidence grows and standards mature, you can adjust the balance without changing the basic contract between applications and the crypto service.
Vendors and hardware platforms are an integral part of this story. A hardware security module, HSM, with limited support for new algorithms, or a smart card platform that cannot evolve, can become its own gravity well. When you evaluate these products now, you need to ask not just whether they are certified for today's algorithms, but how they will handle tomorrow's. That includes understanding firmware update patterns, certification timelines, and support policies. A product that looks secure today but cannot evolve may leave you stuck just when you most need flexibility.
If you do this work, the PQC shift becomes one of many evolutions in your trust stack rather than a one-time cliff. You will still face hard choices about timing and priorities, but you will not be trapped by old decisions that assumed cryptography would stand still. The question then becomes how to embed these ideas into the mechanisms that actually decide what gets funded and built.
Roadmaps are where intent meets reality. If PQC appears only as a separate security slide, it will usually lose out to revenue-generating features and dated compliance obligations. To make progress, you have to weave PQC into the same planning processes that handle platform upgrades, technical debt reduction, and major product bets. The more you can frame PQC as part of keeping your trust infrastructure current, the less it feels like a speculative side project.
One pattern that works in practice is to create a small number of clear PQC objectives and attach them to existing streams of work. You might tie crypto agility for internal service-to-service traffic to the platform engineering roadmap. You might connect quantum safe protection of long-lived archives to your data and backup strategy. You might assign partner and vendor readiness to the third-party risk and procurement program. Each objective needs an owner, milestones, and budget inside an existing lane rather than as an orphaned initiative.
With that structure in place, you can define a few simple indicators of progress. You might track how many critical systems now use a crypto platform instead of embedding algorithms. You might look at what percentage of long-lived, high-interest data is under quantum-safe or hybrid key management. You might count how many strategic vendors have articulated their own PQC plans and how those align with your needs. The specific metrics matter less than having a tangible way to see that PQC is moving forward alongside everything else. Communication ties everything together. Boards and executive committees do not need a deep dive into lattice-based cryptography, but they do need a clear narrative. They should hear that quantum risk is real for particular kinds of data and systems, that you have identified where it matters most in your environment, and that you are integrating mitigation into existing investments. The message is not, we are dropping everything for quantum, but we are making sure our trust foundations can evolve over the next decade.
Regulators will increasingly ask how you are planning for PQC as part of broader resilience and risk management discussions. Being able to explain your portfolio view, your focus on long-lived data, and your roadmap for crypto agility will matter in those conversations. Inside the organization, architects and product teams need clarity that PQC is not a surprise rewrite waiting to ambush them later. It is a set of design expectations and decision checkpoints that they can plan around now.
When you bring this all back to that roadmap room, the conversation feels different. Instead of arguing about which year quantum will break your cryptography, you talk about which data sets you would most regret having harvested and decrypted in the future. You talk about where your crypto gravity wells are and what it would take to loosen their grip over time. You talk about building crypto agility into the platforms you are already funding so that this shift and the next one after it look like manageable maintenance rather than repeated emergencies.
At its heart, post-quantum planning is about learning to steer through a foundational change without freezing. The danger is not just an eventual quantum breakthrough. It is the combination of long-lived data, rigid trust systems, and organizational paralysis. When you see PQC as an all-or-nothing cliff, paralysis is almost guaranteed. When you see it as a portfolio of decisions about where and how your cryptography anchors trust, the path forward becomes more manageable.
For you, as a leader, the useful questions shift. Instead of, can we ignore PQC for a few more years, you begin asking, which decisions today would we regret if an adversary decrypts this traffic in 15 years? And where are we locked into cryptography that cannot evolve? You do not need a giant branded initiative to start. You need a series of pointed conversations with your teams about crypto gravity wells, long-lived data, and the design and roadmap choices that will either trap you or free you later.
Those conversations, backed by a realistic map of your estate and a commitment to crypto agility, are what break post-quantum paralysis. They turn quantum uncertainty from a reason to defer into one more factor your organization knows how to manage over time.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.